I'm Stefano Parolai. I'm a seismologist, I would say. And I started my careers many years ago in the University of Genova in Italy. And I was mainly working in the field of seismic tomography at the time. And I was mainly dealing with the seismic tomography and PN waves tomography. So I was making studies about the lithostenospheric structure and crust. Then after some years, I moved more in the direction of applied seismology or engineering seismology, mainly working on site effect studies, using both seismic noise and earthquake data, also numerical simulation. And then with time, I moved more and more in the hazard field and even risk analysis. And in the last years, I dedicate part of my research time to, let's say, real-time seismology, early warning, and rapid impact of earthquakes. So I was spending quite a large part of my career in Germany, in Geoforschungszentrum. And then since now 3.5 years, I'm back to Italy, and now I'm the director of the research, seismological research center of OGS here in Trieste, and the CRS has also a center in Udine, where I'm actually I'm in this moment. So if someone has any questions also about me, please make questions and the career. You can make any questions you like during the course, any curiosity and whatever. So first point, we start with a very basic. We will deal mainly with waves in our course. And we will see different kind of waves. I think most of you know what we are talking about. We will have both body waves and surface waves. And you know that body waves are mainly classified as P waves and shear waves. The P waves that you see here is in this very simple simulation are just waves in which the particle motion consists simply of alternating of compression and dilatation in the direction parallel to the direction of propagation. We know, if someone of you has already worked with seismograms, P waves are generally the first arrival on the seismogram and with smaller amplitude with respect to the secondary waves that we will see later. This is an example of shear waves. You see that in this case, the particle motion is transverse to the direction of propagation of waves. And generally, you can imagine if we are in a more realistic situation, we would have to turn this small model, let's say, nearly to the vertical. So generally, since the earthquakes are happening in the underground, in the deep part of the earth, when the waves are arriving to the surface, shear waves are mainly causing this horizontal movement of the ground. And the shear waves have larger amplitudes and are generally the cause of most of the damage that we see and that we register in our building structures. There are other kind of waves which we will deal with, in particular surface waves. Traib knows them very well, for example. Here is just an example of the particle motion of the Rayleigh waves. You see that the direction of the particle motion is generally elliptical, and it's elliptical and longitudinal to the direction of propagation. An important characteristics of this wave is that they are having larger amplitude close to the surface. That's why they're surface waves, with the amplitude of particle motion that is decreasing with depth. Rayleigh waves can also exist in homogeneous medium, but if the medium is not homogeneous, so the velocity tend to increase with depth, like generally is happening in the real Earth, Rayleigh waves can be dispersive. So it means that different frequencies propagate with different velocity of propagation. And this effect that we will see several times during the course is due to the fact that longer wavelengths penetrate deeper in the Earth interior, where the velocity is generally larger, and therefore propagate with higher velocity, higher average velocity, let's say, than the high frequency, which have smaller wavelengths and propagating close to the surface, where the material has lower velocity, and therefore they propagate with a lower velocity. And this effect is called dispersion. In the case of surface wave, we can also enter the love waves. You see already here that in this case, the ground shaking, the particle motion, is orthogonal to the direction of propagation. Also in this case, the largest amplitude of motion is closer to the surface, and the amplitude tend to diminish going in depth. Love waves are generally existing in stratified medium, so we need layering, and are mainly related to the multi-reflection of shear waves, in particular SH waves. That means shear waves polarize on the horizontal plane. It's all okay till now? No question? I think you all know this. An important characteristic is also, if you go to the attenuation, that even if the quality factor could be homogeneous, for example, quality factor that is describing the dissipation of energy in due to wave propagation, even if a medium would be layered with quality factor frequency independent, love waves in this case would show a frequency dependent quality factor because they are affected by the different layers in depth. So another important concept that I try to show here is the concept of phase velocity and group velocity, which is very important, especially when we are dealing with surface waves, like Rayleigh waves that we will analyze during the course, because are kind of waves that we will try to extract either from active source experiments or passive experiments. In this diagram, you can see 3 different frequencies from the top to the bottom. You see with larger different, smaller frequency to the top, an intermediate frequency in the middle panel, and then a higher frequency in the third panel, going from the top to the bottom. On the bottom panel, the very bottom panel, you can see just I report the summation of the 3 nearby frequencies. What you see from this small movie is that the lower frequency that is on the top is starting later. You can just wait here. You see it's arriving later. The highest frequency on the third panel arrived before, but you can immediately see that the lowest frequency is arriving as first at the end of the panel, so has a larger velocity than the other frequency. So it means that the 3 frequencies that we are reporting in this diagram, they have different phase velocity, so the velocity for each frequency. But if you look at the very bottom panel, the combination of a nearby frequency, the group velocity, you can immediately notice that this perturbation altogether has a velocity which is lower than the velocity of each single phase. So it starts nearly simultaneously with the first frequency, and it's arriving nearly as the last one at the end of the bottom. So during when we will analyze Rayleigh waves, we will mainly focus on the phase velocity. So we will try to extract the velocity at which each single frequency is propagating in the ground. All clear till now? If someone has questions, can stop me. Okay, there will be a lot of analysis that we will see, especially in side effects. And most of this analysis will be done using the Fourier transform. So what is the concept behind this Fourier transform? So as you know, we are recording seismograms. So we will deal with seismograms, can be recorded by velocimeters if you are recording velocity of the ground, can be recording in acceleration if we are recording strong motion, for example. I heard it from some of it's mentioned, or we can even measure displacement with respect to the time. Okay, this time series have a lot of information inside of them. And generally to study or to extract this information, we don't work directly in the time domain. We prefer to work in the frequency domain. And for doing this, we use the Fourier transform. It means we decompose the signal in a series of harmonic terms that all together are able to reproduce, let's say, the original signal. So you see here, for example, a very simple seismogram that can be described by a summation of different sinusoid, tensor, sinus or cosinus, that have different amplitude, as you can see here, if you go in the vertical direction, different frequency, you see on the top, longer period and lower frequency, and also different phase. So it means you see each one of these sinusoid is starting from the beginning with a different, in a different point. In some cases, it can be close to a maximum. It can be close to a zero. Do you see my mouse? No, I guess. Do you see it?
Yes.
Okay. Sorry, because I was not sure you could see it. So in some cases, you see, you can have a minimum, you can have nearly a maximum, and so on. So it means you can move in some way these sinusoids in time, and this movement in time, we will see it's equivalent to a change of the phase of the signal. So it means phase is telling us how much we are shifting this sinusoid in the frequency domain. So, of course, we can describe the Fourier spectrum in a bit less qualitative way. And if you look at the expression on the top, GDT can be our signal in the time domain, and the Fourier transform of this signal is just expressed through the integral of GT multiply the term, which is, the exponential term here is E omega t integrated over dt. This exponential term can be simply written in the form of a complex number, where we have a real part, which is the cos of omega t, plus an imaginary part that is described by the sinus function as function of omega t. So theta is just omega t in our case. So with some mathematics, we can rewrite then the Fourier transform, d of omega, as the integral of gdt multiplied a cos function plus e sinus of omega t. So in a very simple way, you can immediately see that we can separate the two parts. We will have a part that is a part of the integral depending on this integral on the cos term, and a part of the integral which is depending on the sinus term. So this is telling us that the Fourier transform of our original signal in the time domain, which is a real signal, so we will have a value for each sample of time, this can be then described as a complex function, complex number where we have a real and an imaginary part. Okay, I think this should be enough clear. So this is quite important. Generally, you know, we are not working with continuous signal. I guess you know a little bit what is a digital signal. Do you have an idea about it? So what is the difference between an analog signal and a digital signal? You are the digital generation, so I'm sure you know it. So when I'm measuring with my instruments, I'm measuring continuously the shaking of the ground, let's say. For example, if I have a seismometer, I have a system which is able to measure the velocity at which the ground is moving. Or if I have a strong motion instrument, someone mentioned it, I'm just measuring the acceleration at which the ground is moving. But I can also use other instruments, for example, measuring the displacement. Okay, but this is a continuous signal, no? What is happening in my instrument? What is digital? Do you have an idea?
It's the discretization of the signal.
Yes.
I mean, we choose an interval of time. We take just at that time the value, a sample of the signal at that time, and we move.
Exactly.
We have to take into account the condition. I forgot about the condition in order to not lose.
We will arrive to this. We will arrive to this.
Yeah, in order to not lose informations from the signal.
We go from a continuous signal to a discrete signal that is making, let's say, rendering our signal as a sort of series of numbers in which we try to describe the original analog signal. So our sensor, in principle, if I think to a seismometer, is moving, is recording the mass movement with respect to the ground shaking, and this is a continuous electronic signal, and this signal is then digitized sample by sample with a certain interval of time, and then in your computer you will get your signal as a sort of time series, as a sort of series of numbers that can be binary or can be ASCII. Okay, so also, this is important.
I think it's the operation. It's a convolution between the signal in the Fourier domain, convoluted.
Yes, we will arrive to this.
By the Dirac
it's the response of the instrument, since it's like a sort of oscillator. Then the signal we are recording is the convolution, you see, between the original signal, that is the movement of the ground, and the response of this instrument. So what we are recording is not the original shaking of the ground, but it's the response to this shaking of the instrument that is measuring it. So if we want to go back to the original shaking, if we really want to measure the acceleration of the velocity of the ground or its displacement, we have to remove later, through the deconvolution, in this case, the response of the signal, of the sensor. And here, I just show an example. So in this case, you see we substitute the integral with a summation. And the Fourier transform of this signal t can be described as the summation of many discrete terms depending on the cause term for the, again, this is in principle for different frequencies, for different period, and sinus term representing the real and the imaginary part of the signal. So you can imagine that you can subdivide your original signal in many sinusoids, one representing the cause part and one representing the sinus part for different frequencies, for different with different amplitudes, and again you see with different shift in time that is representing the phase change of the signal. Important, you see that, of course, the sinus and the cosinus term are shifted of 90 degrees, so of half p. This is because one is a cos and one is a sinus term. So which information we can obtain then from the Fourier spectrum? Well, this is quite important, especially in side effect analysis, but I would say in all seismology, because starting from the original signal, we can, through the Fourier transform, obtain information about how strong is the amplitude of each frequency composing the signal. And this is the information that is mainly used in most of the studies, so the information about the amplitude, but we have also information about the phase of the spectrum, and the phase that was corresponding in the time domain to the shift of the signal is just calculated as the ratio between the imaginary and the real part of the Fourier transform. So we have two important information that we obtain from the Fourier transform. We have an information about how strong, how energetic is each frequency in the signal, and an information about the phase. So if we go back in the time domain, it's an information about at which time this frequency is arriving in our time series. And this will be an information that is we will use a lot in the following analysis, because most of the analyses that are relying on the surface wave usage are mainly trying to estimate the velocity at which the surface waves are propagating through the information on the Fourier phase spectrum. So try to keep this in mind about this important point. The Fourier transform has also some important properties that in seismology are used very often and are very helpful, especially for simplifying some of the calculations that we are doing in our daily routine. First of all, if we have two signals, two time series, can be two seismograms, you can see it in this way, or can be the shaking of the ground plus some background noise, the Fourier transform of the summation of the two signals is equivalent to the Fourier transform of the first signal summed to the Fourier transform of the second signal. So this is an important property that we are very often using in seismology. Then there is another important property, that's that the Fourier transform of the derivative of the signal can be calculated just simply taking the Fourier transform of the original signal and multiplying it for E omega. When we use this property, just imagine, for example, that our sensors are measuring the velocity of the ground. It's just a seismometer. So I get velocity, but one of you who is an engineer, maybe it's more interested in acceleration. Acceleration is just the derivative of velocity. So one way in which we can calculate the acceleration, for example, is to calculate first the Fourier transform of the velocity of the ground, and then we multiply for E omega. So in this case, we will have an inversion of the real and imaginary part of the spectrum and of the sign, and we have automatically the Fourier spectrum of the acceleration. If we apply the inverse of FFT, we can go from the frequency domain to the time domain and obtain our time series. This is just a way, but very often in engineering, we have the contrary problem. So we record acceleration but we want to calculate velocity, or even more and more in the last years, the displacement. And this is done following the inverse procedure. So instead of multiplying for e omega, if I want to go from velocity, so acceleration to velocity, I have to divide for e omega. If I want then to go from acceleration to displacement, I have to divide for e omega square to take into account the double integration. So there is a full consistency, let's say, from what you can do in the time domain and what you can obtain in the Fourier domain. Another important property of a Fourier transform is related to the shift in time of the signal. So you just imagine you have a pulse at a certain point, and then you move in time of a quantity A, this pulse in your time series. When we can have this example? For example, just imagine we put two sensors in the ground, and then you go to a few meters far away from the first sensor, and you just use a sledgehammer to generate a signal. Then you will have a signal, maybe just a simple pulse, arriving at the first sensor. And then this pulse will propagate to the next sensor, to which it will arrive a little bit later. So if you plot these two recordings, starting at the time of when you use the sledgehammer, you will see a time series with a pulse and another time series with a pulse at a time which is a little bit late. So it's like if you're adding a quantity, for example, A, a certain amount of time of delay to this pulse. Okay. The Fourier transform of the second pulse, which is shifted of a quantity A, or can be anticipated, of course, depending on which reference system you're using, it's equivalent to the Fourier transform of the original signal. So for example, of the first signal, multiplied a term E minus E omega A. So you see immediately, we found again the term that we saw before that can be separated in a cos term, omega A, plus E, so it's a product for the complex number, E sinus of omega A. So we see here that the time shift A correspond to a phase difference in the original signal. Why a phase difference? Because if this is a cos term plus a sinus term, the amplitude for which I multiply each frequency is equal to 1, is sinus square plus cos square. But this term is adding a phase shift related to the ratio between the sinus and the cosinus function. Okay, so each frequency will be shifted of the amount theta that depends on the frequency itself and on the amount of time. So shifting, moving a signal in time correspond to a phase difference in the Fourier. And the amount depends on the time and on the frequency. And I can calculate the phase difference. This, you can imagine, is a very important property that we are using in seismology a lot to measure, for example, the velocity of propagation of waves between two stations using the recordings. But we are using the same property also for the propagation of waves in buildings or in buildings and soil. Nothing is different from this. And then we come to the other property that was correctly mentioned before by Terek, the convolution. So if you imagine that F1 is the recording, the shaking of the ground, F2 is the response, let's say, the time domain of a seismometer, or can be also an oscillator or whatever, to your input shaking. So what we are recording is called the convolution of F1 and F2. The convolution in the time domain can be calculated through this integral. But it's easier to calculate this through the Fourier transform. So the convolution of two signals is nothing else but the product of the two Fourier transform of a signal. So I can calculate first the Fourier transform of the first signal. I can calculate the Fourier transform of the second signal and just multiply them. If I want to see the results of this in the time domain, I can just calculate the inverse transform of this convolution. Generally, as you can imagine, in seismology, we are dealing with a different problem. We don't have, for example, what is the source generated signal. We don't know the signal, let's say the green function, the propagation function in the time domain. And we don't know, for example, the site response, how the site is modifying the shaking just below the surface. These are all three different, let's say, imagine signals that are convolved together, and even with the instrument, to generate our final seismogram that we obtain in our laboratories. But generally, we want to do the contrary. We start from our seismogram, and we would like to separate each contribution from the source of the earthquake, from the propagation through the crust, from the site, and also the instruments that maybe we should know quite well.
Please,
so generally,
Professor,
yes.
I don't understand the word site. What do you mean by site?
Site is that when waves are propagating, we will see it later. You have a propagation starting from the source, that is your initial signal. This is propagated to the crust, let's say. And then depending on the local geology, just below, let's say, your point of observation, you have some modification of the shaking due to the site. So we call it site due to the last part of the propagation in the shallow geological layers. Okay? And also this can be expressed through what we call a transfer function. So how the signal is modified from the propagation from here to the surface. So generally we have this problem and we want to separate this. Okay?
Okay.
And the easiest way is to do it not in the time domain. Otherwise, we will have a very complicated integral and we should go back from the integral. But it's much easier if we describe this as the product of a different terms. And even if we take the logarithm, this can become a linear system of equation. So this will be the summation of the logarithm of the first Fourier transform plus the logarithm of the second Fourier transform. So it's something with which we can deal quite easily. And this is exactly used in most of the problem where we are trying to separate from the observation the different contribution of the source, of the path that, for example, can be the attenuation, let's say, function through the crust, or the propagation, including attenuation through the crust, and the propagation in the last geological and the shallowest geological layers. Okay? So we have to remember these properties.
Okay.
Do you have questions? Anyone else? Okay. So just make a very simple example. We have now three simple signals, three sinusoids. We will call it, let's say, 2, which is this pink one with lowest frequency, let's say, if on the X you have the time domain, and with the largest amplitude. Then we have a sinusoid that for sake of simplicity, we call free, with a blue line, which has a slightly smaller amplitude, and then higher frequency with the sinusoid green. So now we can generate a signal, which is the composition of a free sinusoid. And you see, combining them, just simply summing them up, you can immediately see the red curve. So this could be an example of signal that is generated by the combination of different signals with different frequency, with different amplitude, and you see here different phase. So the green is starting from the maximum, the blue from the minimum, and the pink in something in between. So if I take the Fourier transform of a red curve, I would expect to see three clear peaks. One at frequency, let's call it 3, one at frequency, we call it 2, and one at frequency that we call 5, corresponding to the green line. So this is the amplitude spectrum of a Fourier transform. So this is the modulus. You remember before, we take only information about how strong is each frequency. And we immediately see that, yes, okay, we see a clear peak at 2, with the largest amplitude corresponding to the pink line. We see a peak at 3 with intermediate amplitude corresponding to the blue line, and a peak at 5 corresponding to the green line. There are also some other small peaks due to some smearing of energy due to the numerical solving of the problem. But what is more interesting is to see that in this signal that we generated, there is also a large contribution with a large amplitude at frequency 0. Where is this contribution coming from? This is coming from the fact that you see the red curve has no zero mean. So while all the other signals were positive and negative having a zero mean, their summation is always nearly positive. And if you remember from this first equation here, for example, at frequency 0, when the frequency goes to 0, the coefficients are becoming just as the summation of the signal and the average out. So it's just cos term is becoming 1, the sinus term is 0, so we will have for frequencies 0 just the summation of the original signal. So since the signal has no zero mean, at frequency 0 we will find the summation of the original time series. And now we come to the discussion that we have done before, the digitalization. So till now it's all clear for everyone, things that you know very well. So it's okay? Okay, great. So another important point that Tarek mentioned before. Generally, we have a continuous signal, but we want to work with numbers in our computer. So we use a digital signal. So it means that our original signal is sampled with at many samples with fixed interval. In our case, since we are working with signal recorded over time, we signal with a step in time which is fixed. And this is what we call our sampling rate, that we will call here dt. So the total duration of the signal is t, big, which is equal to the number of samples multiplied the sampling rate. When I calculate the Fourier transform, I have to consider two important things. the minimum frequency that I can observe in my signal and the step in frequency of my Fourier transform is depending on the total duration of the signal. I give you an example. If t here it's 1 second, my delta f, so my step in frequency domain of a Fourier transform will be equal to 1 divided t. So will be 1 hertz. If I will have a longer window, let's say 10 seconds, my step in frequency in my analysis will be 1 divided 10, so 0.1 hertz. So since the Fourier transform is it's providing you the information all over the whole window that you are analyzing, it's clear that if you want to have lower frequency information and with larger spacing, you have to increase the window of analysis. If you want to have, let's say, a more precise analysis of a signal, let's say over a very short window of signal, you have to narrow the window, but then it means you are losing information or in the step of the Fourier transform. There is another important things that we have to remember, that is the limitation imposed by the sampling rate. So if our sampling rate is, for example, df, it means that I can only retrieve for a maximum a frequency which is half of df for the total number of samples divided 2. So just to give again an example, if I take 100 samples per second, so in sampling, let's say at 100 hertz, the maximum frequency that I can see in my system, in my signal after digitalization will be 50 hertz. If I increase the sampling rate to 200 hertz, I can see still 100 hertz, so half of the sampling rate. Why this is happening? Why, you can see it here. So if you have a sinusoid, it's a very simple case like this one. Let's assume that the time scale here it's 1 second for each unit of time. In this case, you see, if I take a too large sampling rate, so my sinusoid here has a higher as the 1 hertz, and if I sample at 1 hertz, when I retrieve the digital signal, I will not be able to retrieve the original red one, but I will have a signal like the blue one. You see? So if I'm not taking too many samples or enough samples, depending on the sampling rate, I can be completely wrong in retrieving the original signal. So the sampling frequency should be at least double than the frequency that I have in my original signal. Otherwise, I have an effect that is called aliasing, and in which you can say I'm inventing, let's say, a low frequency in the original signal that is not existing. Okay? What is the problem? The problem is that when I go in the field, I don't know a priori, I don't know what is the frequency content of the signal related to the shaking of the ground, right? Who tell you? So generally our instruments, what they are doing? They are recording the shaking and then they digitize, like we said, the signal. But if in my original shaking, I have a lot of high frequency and my sampling rate is too low, I would generate a, let's say, a fake in the digital signal. To avoid this, seismic instruments, they use a filter, for example, in different ways, in which, let's say, the original signal is a low-pass filtered before there is a digital conversion. So if you, again, decide to have a sampling rate of 100 samples per second, which is quite standard in seismology, you have to filter the signal before, and generally this is done with 0.8 of the Nyquist frequency. So if it's 100 Hertz, then the Nyquist frequency we said is 50 Hertz. 0.8 of 50 Hertz will be 40 Hertz. So we will have a filter that is cutting before digitizing all the frequencies higher than 40 Hertz. And then on what remain, you can see it in this way, then it is applied the digitalization. And we get a digital signal in which we do not expect to have aliasing. Okay? All clear? So there is also a very nice correspondence to what we see in the time domain and what we can see in the space domain. So if we have a signal in the time domain, we said we have samples every dt, and when we calculate the Fourier transform, we will have a step-in frequency, a maximum frequency, which is the Nyquist, that depends on 1 divided dt, and divided 2, and we have, sorry, it's in German, this, okay, omega frequency, which is equal to pf, where the frequency is related to the period of our oscillation. So in the time domain, what we are doing, just imagine we are here. This is my sensor. I'm recording in the same point the oscillation. So I'm just going, for example, for the vertical movement, I'm just going up and down. And my period here is the period at which I have my oscillation in the same point. But you can find also something equivalent in the space domain. So just imagine you are an observer here and an observer here or here. You have a propagation, a wave, which is arriving and it's propagating, moving first these particles and then moving all the other particles while it's propagating from the left to the right. Okay, so if we look at the position of each particle in the space and not in time, what you can have, you can also sample in time in the space your signal with many sensors at consistent distance. Okay, like you are doing in time. Now you put many sensors that are your sampling at a certain position along the wave propagation, and you can obtain the value at each instant of time of the amplitude of movement of your ground. So in the case before, you fix one point in space and you look only at how this point is moving in time. In the case below, the waves are propagating in the ground. You frozen the time, and at the same instant of time, you look at how in different points the ground is moving. Clear? So in this case,
please.
Yeah.
For the previous slide, the previous below here, it means if we froze the time, it means we have different instruments in
exactly.
in our field.
Your
here.
sampling will be given by many instruments. Just imagine you have one instrument along this line every 1 meter. No?
Okay, okay. Okay.
And each one of these instruments at the same time will give you different value because it's the value that is recording exactly at the same time. And will be different because the movement of the ground will be different. Okay?
Okay. Okay.
Effectively, if you substitute dt, which is your sampling in time, with dx, which is the sampling in space, because you have one instrument every meter, then you can also have a Nyquist frequency in the frequency domain, in the space domain. So it means if your sensors will be too far away, like in the case of the sampling in the time domain, you can have aliasing because you are not able to correctly retrieve the movement of the ground. So just imagine you have one sensor here, one sensor here, one sensor here, you will have nearly a straight line. Okay? So the same aliasing that we have in the time domain, we have it in the space domain. And if we look at the amplitude of shaking in a fixed time, but for different position x, then we will not have any more the period, but we will have what we call the wavelength of a signal. So the wavelength is equivalent to the period in the time domain. And if we take 2p divided the wavelength, then we obtain the wave number, which is equivalent to the frequency in the time domain. Okay, so we have equivalence in a way. We can see the signal either in one point, but for different time, or in different point at the same time. Clear? And we have this equivalence. So we have, of course, the two things are mixed together. It's just our mind that for simplifying things can use this approach. Okay, so this is something that we have to keep in mind because when we will try to study the underground, we will have digital signals. So showing at each sensor how in time the shaking is changing. But these digital signals will be recorded at many sensors in the space. So for each one, we will not only have, they will altogether provide us also a view of how the shaking is changing at the same time in different positions on the Earth. Okay?
Okay.
Now, very simple parameters, just to relax a little bit. These are just recordings of the same earthquake. What is the difference? On the top, we have the recording in acceleration. In the middle, we have a recording in velocity. And on the bottom, we have a recording in displacement. So if we take the maximum value on the acceleration, this is what we call peak ground acceleration, very simple. When you will see hazard, very often you will hear about PGA. It's nothing else but the peak in the acceleration that you record. At the same time, we have a peak ground velocity. That means the maximum velocity of the ground that was measured during this earthquake and in this place. And then we will have a peak ground displacement that is representing the maximum displacement that is recorded on the ground. You see that the shape, this is the same recording, is quite different depending if we are in acceleration, if we are looking at the velocity of the ground, or if we are looking at the displacement. Can you imagine why? No idea? So generally, if we assume a very simple, let's say, shape of the earthquake spectrum, and we look at the displacement, we can imagine that the earthquake spectrum has a shape like this. So for the low frequencies nearly flat, then above what is called the corner frequency. Some of you, I think, heard it by Fabio Romanelli, I'm sure. The high frequency spectrum is decaying. This is in displacement. What is velocity with respect to displacement?
It's the derivative.
Yes.
Yeah.
And what we said that will happen to the Fourier spectrum if we calculate, if we want to go from displacement to velocity, how we calculate, how we can calculate the derivative of the original displacement spectrum.
We multiply by an exponential E
We
omega
multiply
I.
for E omega.
Yeah. E omega.
So what means this? Omega is nothing else than 2p for the frequency. So what will happen? For the low frequency below 1, if I multiply for something small, because it's smaller than 1, the spectrum will decay. But for frequencies larger, let's say than 1 hertz, even lower, because there is the factor 2p, the spectrum will increase in amplitude. Do you agree?
Yeah.
Okay, so now it means that I go from something which is dominated by low frequency, and you see it in the displacement, to something that starts to be dominated by intermediate frequencies, right? My peak now is close to the corner frequency, is where I have a maximum. Do you agree? And what's happened now if I go from velocity to acceleration? I have to multiply again for E omega, right?
Yeah, yeah.
So the low frequency will be even diminished, and the high frequency will become predominant.
Yes.
And that's exactly what you see here. The acceleration, it's mainly dominated by the high frequency components, velocity by the intermediate frequency, and the displacement is mainly dominated by the low frequencies. But this is exactly the same earthquake. Is it clear?
Yeah, yeah.
This is very important. It's really important because when we will work on the spectrum and we will try to separate the effect of the source of a path or site effects, like we discussed, it will not matter the site response if we are in displacement, in acceleration, or in velocity. Each component will be the same. But if we look at the time domain, we can have results very different. Because, like we will see, maybe some of the effect will change the amplitude of shaking only in the low frequency part. So if I look in acceleration, I will not see this effect. Or if I will have a local effect that is only modifying the high frequency part of shaking, it will affect the PGA, but it will not affect very likely the PGD. Always the same. So we have to be careful if we are working in the time or in the frequency domain. We have to keep always this in mind. Is it clear? Engineers, and some of you are an engineer, are not using very often Fourier spectrum. Now it's becoming more popular also for engineers, but it's a standard practice and also for design that another quantity is used for representing, let's say, the shaking of an earthquake. And generally, this is done through what is the response spectrum. It's the response of initial ground motion. This is just the shaking of the ground. Is the response of an oscillator, a single degree of oscillator, so like a pendulum. How this is reacting to the input shaking. So ADT is the shaking, and we look at how the single degree of freedom oscillator is reacting in terms of acceleration or displacement or velocity. Okay, this is very important. The oscillator will have its own frequency of oscillation or its own period, here indicated by T, and also a certain damping, okay, like every oscillator. So how does it work in principle? In a very simplified way. Just imagine that we take this shaking, we put it below a small oscillator with a small period, so high frequency, and we check the movement versus time of this oscillator. The movement will be strongly, let's say, will have a strong sinusoidal component close to the resonance frequency of the oscillator. So we look at the time series that is generated, and we take, for example, the maximum here, if we look at the velocity. And we go in the diagram, we report the period, in this case a short period, and its value that the value that we recorded here. Then we change the length of the oscillator. And this will have a different period because it's, you see, it's taller. So we'll have a longer period of oscillation, and you see it here. And we take the maximum value. So for this period, we report the other amplitude that we record. And so on for many theoretical oscillators. So if we look at all these frequencies, what we will get is what we call the response spectrum, where in the x-axis, we have the period of the oscillator, and in the y-axis, we will have the maximum oscillation for that period. That can be in terms of velocity, or in terms of displacement, or in terms of acceleration. So it's something a little bit different from what we have seen before. Okay? So generally, the general idea behind this is that we have a single degree of freedom oscillator with a dashpot, with a certain damping, with a certain mass, and we can describe the motion both of x of t, which is the relative motion of the mass with respect to the ground. Epsilon of t is representing the absolute motion of a mass with respect to the fixed reference that is below, and ADT is the absolute acceleration of the ground with respect to the fixed reference. So the equation of motion is the same that you have seen before, where omega, which is the natural frequency of the oscillator, so this is nothing else like a pendulum, depends on the stiffness and the mass. Then we have the period of the oscillator, and we have also what is called the fraction of critical damping, epsilon. This is the general solution, where you can immediately see the importance of the frequency in scaling factor and of the damping, but also that the damping is entering in the integral, but especially that you have a sinus term that depends on the damping and on the frequency of the oscillator. Okay, if I solve this equation, it's a convolution for each frequency of the oscillator, I can calculate, for example, the displacement. I look at x. So I will have the maximum value of x for each frequency of the oscillator that I obtain. And if I do it for many frequencies, I will get the relative displacement response spectrum that is defined as SD. If I look at the velocity in the solution, I will obtain the relative velocity response spectrum. If I look at the acceleration relevant to the absolute motion, I will have the absolute acceleration response spectrum. Very often we calculate the relative displacement spectrum, and then with a sort of trick very similar to what is done for the Fourier spectrum, we obtain the velocity spectrum multiplying the displacement for omega. And we get what is called the pseudo velocity spectrum. If we calculate for omega square, we will obtain the pseudo acceleration spectrum. There is a slight problem that the pseudo velocity spectrum, it's a large approximation because you see we have a sinus term. So when we multiply for omega, we are not inverting, so this should be proportional to the cos term. The second derivative to acceleration will give us again a sinus term. So the step from the relative displacement to the pseudo acceleration spectrum is relatively correct. There are more difference between the relative velocity response spectrum and the pseudo velocity due to this approximation of simply multiplying for omega n. Why we do this? Why in engineering practice this is used very often? Because in a simplified form, you can imagine that a building can be considered as a sort of oscillator. An oscillator that will have not only a first mode of oscillation, this is just a building where we made measurements in Istanbul, and these are results that we will see during the course. A building can be considered as a sort of oscillator with different modal shape of the formation. This is the first mode, where you see that the amplitude of oscillation is increasing, going up in the building, and you can clearly see it very well here, where you have peaks in our measurement increasing with the height of the building. But you have also a second mode of the formation, in this case, that you can also retrieve it in our measurements. You see that the amplitude is increasing till a certain level of the building, and then diminishing, going to zero, and increasing again. So that's the reason a little bit behind this way of looking at the data. Clear? Of course, you can have for translational modes much more variation, and especially for tall buildings, you can have several modes of deformation of a structure, and not only translational, of course. You can also have rotational modes. So what is happening to the response spectrum if we change the frequency of oscillation and if we change the damping of the oscillator? So this is my input accelerogram. So just acceleration of the ground due to an earthquake. Now let's see how a single degree of freedom oscillator would react to this input motion. I plot here the response for different oscillators with different period or frequency. So this is high frequency, intermediate, low frequency, but for the same level of damping, of fractional critical damping. This is 2%. You see that you can immediately see that the high frequency oscillator is responding with high frequency and with a moderate peak amplitude. The intermediate has a completely different frequency and a different amplitude, and so on for the lowest frequency. To this right panel, I show you another example. Here we have the same period, so I'm not changing the period, but I just change the damping of the oscillator. So the period is always 2 seconds. So what you see is that when the damping is 0, That means nearly no damping. So the oscillation is very large and is continuing over time. When I increase the damping, I have a diminishing of the maximum amplitude, but also a diminishing of the oscillation. When the damping is becoming, for example, 5%, which is a standard value in engineering, we have a further decrease of the amplitude and a much shorter duration of oscillation due to the larger damping of the signal. It's all clear? So we have more dissipation. So if you take these values, you see for different oscillators, but the same damping, you take the maximum. In this case is in displacement. You have a spectrum in displacement. And this is just the shape of the spectrum as a function of period. So like I said you before, and like we were seeing in the data, longer periods are dominating the displacement. If we calculate also the pseudo velocities and the pseudo acceleration, we see that the velocity is dominated by intermediate periods and the acceleration is dominated by short periods, so high frequency, exactly what we were seeing in the data before. Okay? You can also have a very simple representation in the same graph. This is what engineers like a lot because it's easy to read. You can report the same spectrum. Here you have the period. If you read it in this direction, you will have immediately the spectrum as a function of velocity. Here you will have a pseudo acceleration spectrum where you can get exactly the value, and here you will have the spectrum in displacement. So it depends on in which direction you are going to read along which axis. So with one representation, it's possible to have a full overview of the different spectral amplitudes. Okay, this was one part of the very basic. Just to finish today, I introduce a little bit the problem, that is a little bit more seismological now. So when we have an earthquake, like in this case, you can have a rupture in the earth crust, for example. This rupture is generating a signal and waves that are propagating through the crust. The propagation can be simple, complicated, depending on the medium. And of course, is also affected by scattering. It's affected by attenuation due to quality factor and dissipation. But what we notice, or my since many years, is that if you are relatively far away from the fault, for example, the recordings that we have close to an area that has both rock side and soft side, that means, for example, sedimentary material, soft material, even if the two recordings are taken at a nearby distance, they can look quite different. Generally, the recordings on the rock side have a maybe shorter duration and smaller amplitude. The recording on soft materials, sedimentary materials, they have much larger amplitude and very often longer duration. Since these two sites maybe are very far away from the source and the propagation can be considered nearly identical until here, this difference in amplitude is generally related to sort of local geology effect, to the effect of the material which is below this. And this is what we call site effects. So this is a site that I mentioned before. All this part is contributing to the hazard that you are measuring at the surface. But we know that buildings are also existing in this area. And buildings are not only damaged by the shaking of the ground, but they can also release waves back to the ground, and they can modify also the shaking in the ground. And this is one of the emergent field that we are studying in Urbesis project, where many of you are part of it. So one of the main tasks in this course will be to study how the local geology, so this last part of the propagation, is modifying the ground motion, and how we can measure this, and if we can include this, let's say, then in seismic hazard assessment. Okay, for today I would stop here. Do you have questions? Yeah, a couple of minutes. It's all clear, was boring? You knew everything, or you are all asleep, or I don't hear you?
Yeah, here. Yeah, it's good.
So it's all clear. Do you have questions?
Professor?
Yes.
I have one question, but not from what you were explaining today. It was just
Okay.
somebody asked me yesterday, and then I was not sure if I answered him properly. So during, like, let's say before the S wave arrival, the animals start to show some unusual behavior, like snakes, rats. They come out, a dog, they bark. Which waves do they feel? Is it P wave or it's another wave?
I don't know. It's a very long and complicated discussion. Okay, there are books and huge infinite discussion about earthquake prediction and animal behaviors. I honestly don't know how to answer precisely to your question.
Mm-hmm.
And I don't know if it's really true, honestly, that all animals are reacting to the arrival of P waves or dogs, especially before S waves. There are some, there has been some test analyzing in details the animal behavior, and some could show some relation between some signals and their behavior. But, you know, one has to be very careful in considering these points, very careful that this is not going in promising a sort of earthquake prediction. Mm-hmm. That's really the risk. I think it's really interesting by the scientific point of view, because of course we have to learn, and there is still a lot that we have to learn about sensitivity of animals, both to electrical signals or other signals. But this is a completely different to who is using this for making a prediction. And when I say a prediction, I mean indicating the precisely when and where an earthquake will strike. Mm-hmm. And this is really the problem. So I would be careful in analyzing these. There was a paper, I think a couple of years ago, of German colleagues reanalyzing all with quite a robust statistic information about animal behaviors. And I think this could be a good starting point, or something that one could read. Mm-hmm. But again, be careful. In science, we need that things can be repeated, can be assessed. We have to have information not only on when something happened, but also when something did not happen. So when a dog was barking, but there was no earthquake, or when there was an earthquake and no dog was barking. So sometimes, you know, you start only from one evidence, or that can be even a coincidence, and you start making a theory out of it. I mean, we cannot exclude anything in science. We have to learn, but my fear sometimes is when this discussion can go in direction of earthquake prediction, that in the sense of earthquake prediction that I meant before, and this could be maybe dangerous.
Okay, yeah, thank you.
You're welcome. No other questions? Chiara, was all clear for you?
Yeah.
Okay. Good. So if no other question, we can close for today, and we see tomorrow then.
Please, Professor, about the slides. Can you send them to us?
Okay, that's a good point. Some are very big. Do you know if, Anna Maria, do you remember last year if there was a FTP site or something where to?
No, from what I remember, I was creating like a shared drive, but it was on my personal account. So I don't know if this is.
Maybe we can ask Karim Audia if it's possible to have a sort of drive where to share the material. If you like, I don't know. This could be, because to send it to all of you, probably I will stuck my email. It could be a bit complicated, but
yeah, it will be good with
possibility.
Yeah, it will be good with the drive.
Maybe we can do it with a drive or something like this. Okay, I will ask first Karim if I have a drive of the ICTP, and if not, I can organize something by my side. Okay?
Okay, thank you.
Okay, good.
Thank you, Professor.
So, see you tomorrow then. Have a nice
Bye.
day.
Thank you. Bye.
Bye bye.
Grazie.
Thank you. Bye.
Chiara?
Thank you.
Ci sono?
Possiamo sentirci un attimo? Ti volevo chiedere un paio di cose.
Sì.
Ok, magari su Meet se vuoi.
Sì.
Ok, bene.
Ti
Ciao.
Thank you.
mando un link?
Sì, grazie. Ciao.